For our last video in this section, it's time to revisit the invertible matrix theorem again. We've looked at this several times in this course so far. The first time we saw it, it was in section 2.6, which is why it has the theorem number 2.6 point something. And here's what it said back then. If A is a square matrix, then if you know one of the following statements, you know them all. It does not say that any of these is true. What it says is if one of them is true, then they are all true. So if you know that A is invertible, then you also know that it's row equivalent to I sub n, which is the identity matrix in dimension n. So it's n by n identity matrix. So it matches the dimensions of the square matrix A. If you know it's invertible, or you know it's row equivalent to I sub n, you know that it has n pivot positions. You know that the equation Ax equals 0, where A is the same matrix we started with, for any vector x, has only the trivial solution, which means that x is also 0, right? That's what that means. It doesn't have any other solutions either. It has only the trivial solution. An n by n matrix C exists, and an n by n matrix D exists, such that if you multiply A from either side with one of those matrices, then you can end up with I sub n. In other words, there's a matrix out there which, when multiplied by A, either from the right or from the left, results in the identity matrix. And lastly, the transpose matrix, A super T, it's not really a power, it's a superscript. The transpose of A is also invertible. So those are the 7 things that we knew, or that we learned back in 2.6. Then in section 3.4, we added to that list. We had invertibility, row equivalents to I sub n, and pivot positions. Ax equals 0, number 4, Ax equals 0 has only a trivial solution. I'm reading now from theorem 3.4.4. Let me change this. 3.4.4, and all the same statements are made. C and D exist, matrices C and D exist. 5 and 6. Number 7, the transpose, is invertible as well. And then we added a number 8, and that was that the determinant of A is non-zero. That is to say, when you take the determinant of the matrix A, the result will not be 0, be some other number. Then, even farther along in section 5.5, so now we're dealing with, I'll use blue here, now we're dealing with something called theorem 5.5.1. And this time, instead of listing the previous 8 equivalent statements, they just said an n by n matrix A is an n by n square matrix, an n by n matrix A is invertible, that's this statement here, if and only if lambda equals 0 is not an eigenvalue. So we can actually add this. We can make this our number 9. This is what we did at the time. Lambda equals 0 is not an eigenvalue. So to clarify that, the reason I can add this to this list is because theorem 5.5.1 says if a matrix is square, n by n, that's the if part. Then the then part is then that matrix is invertible if and only if lambda equals 0 is not an eigenvalue. Okay, so I've said that A is an n by n matrix. If this is true, then this is true. So I can say if A is an n by n matrix, if number 1 is true, then number 2 is true. If number 3 is true, then number 7 is true. And what I've added here is if number 1 is true, then number 9 is true. And because it's an if and only if statement, it also says that if number 9 is true, then number 1 is true. And if number 9 is true, implies that number 1 is true, and number 1 implies that number 1 is true, implies that, say, 4 is true, then 9 implies 4 as well. So it just kind of fits in the rest of our the work that we've done with this theorem. Now we're going to take a look at the invertible matrix theorem as it's expressed in theorem 6.5.7. So that's for this section. The following statements are equivalent. For an n by n matrix A, the following statements are equivalent. Number 1, these are in a different order for some reason, but they're all still there. Number 1, Ax equals 0 has only the trivial solution. So that is number 4. Number 2 in the theorem 6.5.7 says A is row equivalent to the identity matrix. So that's the number 2 here. The third one is A is non-singular. That is, A is invertible. So that takes care of number 1. The determinant of A, number 4, the determinant of A is not equal to 0. It's written slightly differently, but it means the same thing. Both the row, I'm on number 5 now, both the row and column vectors of A are linearly independent. I don't see that here, so we're going to have to come back to number 5. Number 6, the row vectors form a basis for Rn. And number 7, the column vectors form a basis for Rn. Those aren't present in the theorem as we see it currently. So number 8, A has rank n. And number 9, A has nullity 0. So 5 through 9 in theorem 6.5.7, in that form of the invertible matrix theorem, are not present in the version that we currently have on the screen. The thing is, if A is an n by n square matrix, then, see the ones that are checked off here? Then A is invertible implies that it's row equivalent to I sub n. But from a previous theorem, we also know that if it's row equivalent to I sub n, then it also has n pivot positions. And it has, there are matrices out there that will let us multiply and end up with the identity matrix. So even though I've only checked 4 of these off here, I can check off the other 4, the other 5, I guess, 2, 3, 4, 5, because each one implies all of the others. If you have one of these, you have all of them. All right, so I'm going back now to 5 through 9 in the version 6.5.7, and I'm going to take a look at what each of those means in turn. I'm going to add them to this list in this form. I'm going to start with number 10. So I'll have 10, 11, 12, 13, and 14. But that used to be in 6.5.7, 5, 6, 7, 8, and 9. Just so we can go back to those. Number 5, which is going to be my new number 10, says both the row and column vectors of A are linearly independent. So if I know the number 1 in my new version, which is Ax equals 0, has only the trivial solution. So this is my old number 1. If I know that, then I also know that A is row equivalent to the identity matrix. So I also know this one here, and that's my old number 2. It's also my new number 2. A is non-singular, that means it's invertible. That's my old number 1, but my new number 3. And what else do I have here? The determinant is non-zero. The determinant is, there it is, number 8. My old number 8 is my new number 4. And because I know any one of those, I know all of the others as well. These are the ones that were not listed. Okay, the ones that are listed that were not listed in the previous version are these ones down here. And that is, let's see, I'll write those out. I'll just write all 5 of them out and then we'll talk about them. Okay, let me read through these, the new pink ones, and then we'll talk about them. Both the row and column vectors of A are linearly independent. So if we start with an n by n square matrix and we know that it's called A, then both the row and column vectors of that matrix are linearly independent. The row vectors form a basis for Rn. The column vectors form a basis for Rn. A has rank n and A has nullity 0. Now remember that just saying that A is an n by n square matrix does not make this statement true necessarily. Just knowing that A is a square matrix does not necessarily make this statement true. What we're saying here is that if A is an n by n square matrix, and if one of these things is true, then all of the others are true. Now, some of these are a lot easier to talk about now because we've talked about rank and nullity. We know what's involved there. Remember that A has rank n comes from finding the number of linearly independent vectors in a matrix. So we're dealing with a square matrix here, and what we're saying here is if A has rank n, then it must be the case that the column vectors form a basis for Rn. It must be the case that the column vectors of A are linearly independent. If A has rank n, then the column vectors are linearly independent. if the column vectors, and by this we mean all column vectors, all row vectors. So we have n column vectors, we have an n by n matrix, right? So we have n column vectors and n row vectors. If all of the column vectors of A are linearly independent, it must be true that A has rank n. If A has rank n, it must be true that A has nullity 0, because the rank plus the nullity has to equal the number of linearly independent vectors. It must be true, if all the vectors and all the column vectors are linearly independent, that the column vectors form a basis. Did I say that one already? If all the row vectors are independent, then it must be true that the row vectors form a basis for Rn. So all 5 of these are interlocked in a way. If you know any one of these, then you know all 5 of them. Better still, if you know any one of these, you know all 5 of them plus the other 4 pink ones, right? You know that this one is true, 1, 2, 4, and 8 are also true. All of these 9 statements are mentioned in the 6.5 version of the invertible matrix theorem. So if I know one of the pink ones, I know all of the pink ones plus the old ones that are also listed in the theorem. Well, but if I know any one of the pink ones, then I also know all of the white ones, right? Because if I know, for example, that, let's see, that A has rank n, then it must also be true by 6.5.7 theorem that the equation of Ax equals 0 only has a trivial solution, right? These are, all the pink ones are equivalent. So if I know, which one did I say? The old, I don't know which ones are new and which one's old. I'm just going to call this 13 from now on. Right? I'm going to use these numbers here. If I know 13 is true, then by the pink version, I also know that 4 is true. Well, but if 4 is true, by the white version, I also know that 7 is true. And by the yellow version, that 8 is true. Well, that's also true by pink, right? And if I know that pink 2 is true, then I also know that white 7 is true, because that's actually listed in both. And if white 7 is true, then blue 9 is true, right? So if I know any one of these, I know all of them. And that is some pretty powerful stuff. It's not listed that way in this theorem, but it really does sort of tie almost everything together that we've been working with this quarter in kind of in one way or another.